Okay, so first off, the topic is querying the wire, building a Postgres protocol sniffer in Go. And it's not the usual topic, right? And it came about from me being curious about several things. So in the era of Twitter, I think sometime early this year slash last year, there was this uproar where people were just coming out with different database implementations. Tiger Dito came out, Anthony Alaribe dropped, a way to lay up Postgres over S3 buckets. Some people wrote SQLite in Rust. Several things came about, and I started asking several questions around what does it take to, do something that has to do with databases, something other than your typical post request, get request, which are also good by the way, but something deeper, something lower. That's better. And yeah, this brought this about. I went on this, discovered it was actually very simple. And my goal by the end of this talk is to help the rest of us and all of us who might not be familiar with this to know how simple it is to actually build low level tools. Okay, so brief synopsis. My name is Chukwuemeka Chukwurah. I'm an alleged senior software engineer. I work at Rocksteady Technologies and we're a dev shop. What we practically do is we're a company in the US, we bring your problems and then we give you technical solutions to your problems. And while I'm not doing that, I'm always representing GDG Cloud Lagos. So it's the cloud community side of GDG Lagos, and we just talk about cloud, DevOps, and cloud native tools. Okay, so this is not your usual slide. My entire talk is a README file because I feel developers prefer README files. So feel free to scan this QR code, and we can do this together. All right. The code implementation is also there. So if you want to also start criticizing my code, there's no try catch there, but yeah, you can do that. All right, so I'm just going to give us time to do that, like just 5 seconds, and then I switch to the actual README. So 5, 4, sorry, 3, 2, 1. We're done. Okay. Okay, so yeah, pretty much that. It's just basically, and what we're just going to explain here is a Postgres aware reverse proxy. And it's not your typical reverse proxy. Your typical reverse proxy which we use these days, they are more or less at the very heart of things. It's either they just proxy TCP connections or they actually understand HTTP protocols. So many of them will be Envoy, Nginx, Kadi, and whatnot. However, a different case comes when you try to talk about Postgres. And I will explain why. We'll explain why it's a different case when it comes to databases, Postgres, MySQL, even though TCP proxy works on MySQL, we'll talk about Postgres and other, very difficult protocols, and why Postgres, I picked Postgres in particular. But in summary, like I said before, what we are going to do here, we're just going to explore Postgres, explore the protocol, and I'm also going to explain why, in my opinion, Go is really the best choice for building such tools. Right. So first things first, let's break some concepts down. What are protocol sniffers? And it's just a LinkedIn English. It's not a serious thing. It's just some tool that understands some instruction and can gossip about it. That's pretty much what you need to know about protocol sniffers. They are not complex, right? Well, officially, I said it's a program that captures, inspects, and sometimes routes messages exchanged between the client and the server. It's like watching two computers talk, byte by byte, and understanding their language, right? So the typical, like what I explained before. And very good examples of this are Wireshark. If you've used Wireshark before, Wireshark pretty much monitors every single packet that comes into your laptop. So once you start it up, and let's say you're looking on, the lookback interface, which is localhost, you will see everything that is actually happening on your localhost. That SMTP server, that macOS spins up, every other server, every other port you use, you get to see them. Should I make it bigger? Should I zoom in? Oh, okay. I'm sorry. Is this better? This should be better now. Okay. Okay, so we have Wireshark, TCP dump. TCP dump is another classic CLI tool. You could also use that to inspect TCP packets on your laptop or on your device, so to say. Then you have PG Bouncer. And PG Bouncer is that very interesting one. And I put PG Bouncer here because when it comes to scaling your databases, one thing they will typically tell you to do is, okay, put PG Bouncer in front of your Postgres, right? Because it keeps your connection, it helps you with connection pooling, and all those several strategies that we use when we're working with scaling databases. PG Bouncer helps with that. But it doesn't really align with what I said about a protocol sniffer. And the truth of the matter is, anything that sits in between two entities and can help relay messages can qualify as a protocol sniffer. Right. And the last one is PG proxy, which I'll show how we're supposed to build it. And just show a very light example of the concept, breaking down the important concepts when it comes to building proxies. Okay, now this is where I start to talk Golang a lot. Why Golang is very, very special to me. And the truth of the matter is, these 2 lines of code here is actually a proxy in itself, because what this will do is it just listens on port 5480, your typical net.listen, and it accepts the first connection, which we know, and in a Go routine, it does this. Now, this in my opinion, is one of the most beautiful things I've seen in Golang, the IO does copy function. And what it does is it just internally spins up this infinite loop that constantly reads from here to here. And pretty much what it reads from is IO.writer, from IO.reader to IO.writer. So if you have a file that constantly gets updates, this code will work for it. So not only do you have the ability to build powerful network systems, anything that is behind the IO interface can pretty much work with this. And that's the beauty of Go. And that's a sniffer, like I said, a full TCP listener and reader in one line, no frameworks, no external dependencies, just the Go standard library. I can imagine trying to do this. Let me not share now. Let's just move on. Some languages will actually tear ACL. That's the truth. They will actually tear ACL. But yeah, now I said something about Postgres being a very special protocol. And the truth of the matter is, it's not your typical protocol. One of the most popular tutorials out there in network programming is how to build your own Redis. And you see it everywhere. And the truth of the matter is, because it's very simple, it's all ASCII, it's all text. It becomes a different case. If you ever try to put this TCP proxy, like this one we just created here, for Postgres, and you decide to print the data that comes from Postgres or from the client, what you see is binary blob. And then you get to understand that, okay, there's a different world out there aside from ASCII. And we come to database where every little byte counts. Every iteration of the CPU counts when it comes to database. Every system call counts. So the thing you want to do is database are products of optimization that has been squeezed out from the lowest points. And you come about this concept of binary protocols. Why? Because they are very much cheaper than text protocols. And they are not human readable. Like I said, they are message sized. So ASCII, for example, if you're working with HTTP will come with HTTP 1.1, then /r/n, you see the next things. Binary protocols would come in numbers, pretty much numbers, and you just something like 5, 4, and we'll show it here. I'm going to show it here in Golang, but it's pretty much going to say, okay, this byte represents the length of the next few bytes. So let's say I want to send select 1. Select 1 is how many languages? How many characters? Select is 6, 1 is 1. And then let's say the space in between is 7. So 6 plus 1 plus 1, that's 8. I could just literally put 8 and then convert those select 1 into their ASCII equivalent. So, and that's literally the representation of select 1. In HTTP, you have to first put some indication that this select statement, then put your delimiters and whatnot. So the good thing about this is binary protocols are then cheaper, they're smaller in size, and the smaller the size, the faster it is to transport, right? That's why gRPC shines, for example. And they are also easier for computers because they're reading ones and zeros. The computer doesn't have to do some, actual mapping from ASCII to numbers and then all this calculation. And because of that, you could also work with, because they're all ones and zeros and numbers, you could work with binary protocols with just arithmetic. So I could jump from index position 5 to index position 7 to start the next few things I want to work on. And that's why binary protocols shine. But they are not human readable. So in a case where you really want the protocol to be human readable, there's that trade-off that comes in. And that's why databases have them. Many of the networking tools we use, HTTP, SMTP, they don't use it. They're text-based, right? Okay, so an NGNS refresher. And I promise this is not a computer science course, but we just have to break down two things. Big endian, most significant byte first, which is how normal human beings are meant to write words. And little endian, least significant byte first, which was a standard that was introduced by, I think, Intel, that caused a lot of problems, and people still complain about it today. But most tools you see out there when you talk about endianness, we actually tend to work with big endian. That's your network byte order, for example, still. But little endian exists, and it's also important to note because when you're working with ones and zeros, you want to know the order in which they came in. Many are times with big endian, but don't make that assumption. Always check. All right, so that's all about it. Postgres uses big endian, and Go makes this explicit. Go also offers the encoding/binary package, where you can also use to handle these things. And we'll show all of them, right? How we'll build this actual sniffer, and we will not have to run. I don't even think I have a go.mod file at all. I don't think I have it. I think everything from the standard library just does everything. Okay, and this is how you read with big endian. So big endian, we have this binary text 04D2, 04D2, 16 and 2F. And I'll show you why that particular number is special. But with big endian, we just converted this to, we're using the big endian method, and we're reading it as a uint32, right? So we're admitting that, okay, this is binary that's coming. We know the binary is in big endian, and we're reading it as a uint32. If you decide to read it as something else, you might have, overflows, right? Just in case. But uint32 is safer. And when you print it out, you have this. When you convert this to actual, text, this is hexadecimal. Convert it to number to the binary. This is the number. And this number might look very, very cryptic, but it's actually, if you see this, when we get to the reason why Postgres put this number, you realize that engineers, those big engineers, are still human beings like us at the end of the day, right? Okay, so Golang. Why Golang? The net and IO packages is arguably the most beautiful standard library in the entire world, in my opinion, because they are built behind the same interface, pretty much. The net and IO packages are what make Go the language for building protocol-aware systems. Unlike many languages that abstract away the network layer, Go exposes sockets as first-class citizens. When you work, if you've pretty much built anything networking in Go, you already know what net.con is. We don't really have to talk much, but you've pretty much seen net.con. You've created your own loop, and your loop has accepted the connection and done something with it. And that's something that is really abstracted away in other languages. In JavaScript, for example, you work with events, and then you do something like on accept of something, and then you process what you want to process. But they hide away all these things. And it seems like in Golang, it's somewhat hidden in the sense of you're not still working in binaries, but you get to know what does it take to build systems that work. And then you start to handle all the if errors, got to nil and whatnot. And that's the beauty of Go. Now, the first thing I want to highlight in why Go is the unified interface, which I've talked about already. And this is the interface for the net.connection. And if you can pretty much simulate this interface, you can pretty much work with this reverse proxy in any method, right? So whether it's TCP, TLS, or Unix sockets, same interface, same code. The next part is composable building blocks. When you combine net.con with IO package writer and reader interfaces, you pretty much have a universal pipeline, which is what we showed here. Here, this is pretty much a universal. I even, am I sharing it? Okay, yeah. You can even see here there's even OS.standard output. I did not even put, ideally it should be another, the server behind it. So from client to server, but I'm even copying it to OS.standard output to show you how composable these things are. Right. The next part, you pretty much have concurrency without pin, and we all know how Go's concurrency is pretty much one of the superpowers. You can just put Go in front of almost any function, and then you have a Go routine, and then you're able to utilize this effect, maximize your system resources because you're using Go routines. The next part is built-in TLS and context control. Now it's the TLS package that comes with Golang, you can pretty much upgrade any net.con into a TLS connection by just wrapping it around with TLS.server, and that's pretty much it. And because of this, you're able to start with the same interface and move the same interface around as you deem fit, and you know that you will not be bothered with how do I adapt this to this feature, or how do I adapt this to this other behavior, because they are all behind interfaces, and that's the beauty of Go once again, interfaces. So more reasons why I prefer it for network programming: predictable resource usage, Go routines scale linearly, not exponentially. Minimalism, the net package encourages understanding of TCP and sockets, and I'm pretty much a fan of there's this particular saying, what I cannot create, I do not understand. Right? When you work with Golang, you pretty much get to understand why people make some of the decisions you make, because Golang puts you into the wilderness literally, and then you have to figure your way out. You don't have one strange function that just does something and you don't understand what happens. It's also portable, as with most general programming languages these days. They cross-compile once and they run everywhere. It's transparent because you get to see every byte that crosses the wire, and you also have to handle it. In summary, what I'll say about why Go is, when you work with Go, you don't actually hide the complexity of networks, you embrace it safely. All right? And Rust guys will shout when they see safely in Go, but you'll be fine. Right. So the Postgres wire protocol, and it's pretty much, it can be quite intimidating, but the more you spend time with Postgres docs, as I've experienced, initially it seemed very intimidating. You open Postgres doc and it's just blue and text and some SQL. It's only when you see SQL, so okay, this is what I can relate to it. But with time, the more you spend time with it, you get to actually realize that these are actually very simple primitives, right? And yeah, they're very straightforward. So this is the Postgres binary wire protocol is our playground. And by the time we explain all the things that we're doing here, the goal is for you to be able to look at these docs. One of the goals, look at these docs and see, oh, it's not as intimidating as it used to be. And it will make it your de facto standard for working with Postgres. I know many times when I work with Postgres and I have problems, the documentation is the first thing I really want to work on, because in our fields, I'm now very conversant with it. And it wasn't the case before. Right, so when you open up you see, like what I was saying now, for example, the table of content table is taking up the entire screen. And look at the actual contents, it's just how many lines. But the more you read it, and we'll get to that part. But the Postgres wire protocol, to come back to what we're talking about, it has 4 sub-protocols. And the protocol, like we know, is just a language that two people understand. It's pretty much a language. We all share the same protocol of English. I'm speaking, you're understanding. Computers are not human beings. Let's exclude AI from this discussion. And then they discuss using protocols. Right. And Postgres, being the database it was, Postgres has been here for a long time. And Postgres was even here before SSL came about. And that's why its SSL process is even this complex. That's why you have the require, you have, what are the other verify CA, verify full, and the other kind of verification for Postgres. And it's because it came out before SSL, and they could not just write it from the ground up again. They had to adapt Postgres to SSL. Sorry, adapt SSL to Postgres, not adapt Postgres to SSL. You get? Okay, so there are 4 sub-protocols under Postgres. The first protocol you want to care about is the startup protocol. And that's what happens when client connects to server, they have their discussions, client says, this is my username and password, server says, okay, I know you, and then I check my files to see if you are allowed to connect. Okay, yes, you can connect. We're friends. I spin up a new process for you, and then you can do your database discussion there. That's the entire startup protocol. Then the other protocol comes to do with querying. When I send a message to the database, what happens there? How then do you read that, okay, I'm trying to make a select statement. How do you know I'm trying to alter this table? How do you know? The several DML and DDL DDL and DML queries you probably run against the database. Then the next one is function call. And function call is this particular one is quite peculiar to Postgres, although we have stored procedures in other languages. But I think Postgres is pretty much one of the first few to actually bring out your own. And function calls is just you being able to have some reusable piece of code that you can call many times. So you think of things like triggers, database triggers, you have the actual function procedures, and you can write it in SQL, you can write it in Python, you can write it in Perl. They have some plugins that help you write Postgres code in Python, Postgres code in Perl, and Postgres code in SQL, of course, that's just Postgres. Then there's also the copy protocol. And the copy protocol is what you pretty much use when you're doing data replication, right? So there is always a master slave. When it comes to scaling databases, you have your replication system. There is one that actually receives the data, and then he has to broadcast this to all the replicas. And the primary use case of replicas is to help you scale. So many other times, the replicas will be serving read request, and the master will probably handle write request. That's like a very typical first-hand solution. And then termination is what happens when you're trying to tear down the connection. So you say, okay, I'm ready to tear down. Okay, you said tear yourself down, and I'll tear my own down. Then remove my life. That's the protocol. Okay, and yeah, a very quick diagram to explain things, because the startup protocol, understanding the startup protocol is the key to building the protocol sniffer in Golang. And I'm going to rush through because I feel like they will soon reach out to me for time. It happens, but I feel like it happens soon. So TCP connect is the first thing that happens, because everything we're doing is all TCP connections, right? We connect to it, we make a TCP connection, and then we start the discussions. So the server makes the SSL request, right? The server, and this is for what we are trying to do here. Server makes the SSL request. Actually, ideally, okay, so the server makes SSL request, the server responds with yes, then there's a TCP to TLS upgrade, and then there's authentication and queries and whatever and whatnot. Okay, so yeah, the client actually sends SSL request. That diagram was I'm sure I'll explain why I said server. Because in our proxy, when we're building our proxy, the client will talk to the proxy talks to the backend. So when I meant server there, I meant the proxy. Proxy makes the SSL request, the backend will tell it something, and I'll show that quickly. The client sends an SSL request, and how does the server respond? Either S or N. S means yes, N means no. Right. And okay, this is the last part, and thank God we're done with this. Okay, so now let's go into the actual implementation, and hopefully if I can explain this in 2 minutes, then I will be able to demo it quickly. So let me see. And yes, in case I can't demo, thank God you guys have the QR code and it works. I promise you it works. Okay, so there's a main function, and it's just the typical net.listen, and then just the typical graceful close down, defer your listener.close, and all of that. And then you have your for loop, and then accept. This is just typical standard network programming. This block is like constant in every network programming you build. You accept, you spin up a loop, you listen on the port, you spin up a loop, you accept the connection, you deal with the connection. That's the typical workflow for network programs in Go. Now, the important part is, one, concurrency comes easily in Go. For every new connection, I spin up a handler for it. So I'm already maximizing my resource usage, right? So going into handle connection, now let's see what goes on there. The first thing you want to do is make sure things close down properly. So always defer connection or close. Now, binary protocols. Let's start breaking it down. Now, the first thing I want to do is for the SSL request is pretty much an 8-byte message, right? And that's why I created a byte and gave it the size of 8. Sorry, a slice and give it the size of 8. Right? And the first thing you want to do is just read from it. Typical reading from a connection. And after you read from it, I'm using this big engine like I mentioned before. And all I'm reading here is the last 4 bytes, from byte 4 to the end of the slice. Remember, it's an 8-byte slice. So from point 4 to the end, I'm reading it. And at the end of the day, my expectation is for, I don't care what is actually coming at this point in time. I want to ensure that SSL request is always necessary. And the importance of this is, if you don't make SSL necessary, if you're doing a reverse proxy, one thing you work with reverse proxy requires domain names, for example. But how then do you do domain names in a system where everything is all binaries and it works with IP addresses? You have to bring SSL into the picture. So whenever I want to make a connection with SSL, I present my SNI, which is my server name, and then using that SNI, I now use that particular logic to then route traffic across. So I know we don't have much time, but it's all showing in I think config.go. Yes, no, not. I think there is TLS.go. And in TLS.go, this is where I just load certificates, and then this is where I actually handle the TLS. And you can see here at this point here, whichever domain name you connected with will show up here as your server name. And it's just pretty much a map of, okay, if you're coming from group 1 at Gophercon local, go this way, go to this backend. If you're coming from group 2 at Gophercon local, go to this backend. And that's pretty much how you can. So that's the importance of SSL. It's not like it's needed, but to have this routing ability, you need domain names at some point. Because if you enforce SSL, you build more secure systems. So that's an extra plus. Okay, and that's pretty much the important part. The other parts that requires are just playing around, knowing how to determine what backend to route to based on the server name. And then we come back here, and after all the long story short, the actual proxy name is still the same 2 lines of code. IO copy. The first IO copy is what goes from the backend into the TLS connection. So I'm doing this in the Go routine, but the original copy is what comes from, I receive from the connect. So the client talks to this. So TLS connection is what contains what the client has brought in. I copy that into the backend. I just redirect it to the backend. And in another Go routine, the backend is going to return a response, and then I just copy that back to the TLS connection. So all of this extra thing is just preparation for these first 2 lines. This 2 lines is the actual reverse proxy, right? And you can test it all out. At the end of the day, I just use a very simple proxy.config file, and it's here. And I just said first DB go to localhost 5432, second DB go to 9876. And both of them are running on my laptop currently. I'm using Docker. So Docker PS, you have both of them running. So if I just go run this proxy, and the thing is, I'm going to use a GUI because I don't want to use PSQL for this quickly, just to show it quickly. And I'm just going to edit it. Now note, these 2 things are actually on my laptop. The 2 databases are on my laptop. But how did I edit first DB to this second? I just use a host file. So when you play around with host files on your laptop, /etc/host, you can give yourself custom domain names and have your own simple DNS on your laptop. So that's what I just played around with. If I look at this connection, you can see here that it's pretty much, it goes to firstdb.local. Okay, no, let's not even do that. Let's just connect. So what we'll do is, we're connecting to the same port. If you look at it, we're connecting to, let me show you. We're connecting to port 7070 in this first one. And then we're also connecting here.
We have the source code, right?
Yeah, source code is available.
Okay, we'll test it. Yeah. We'll go to test it.
Okay, yeah. So no problem, you guys can test it.
Round of applause for Chukwuemeka. How can I make this? Thank you very much.